So, it's been about a year since I did my last upload. I have been working on those projects as I stated in my last video, but problem is I've been struggling this past year, both with health and financially. I've only just really got back on top of things, got things stable again. I am still working on those three projects, most specifically the Lyrebird recreation project, but it's a huge undertaking, that project, because of what's actually involved. And I've got to a point where basically I'm going to start getting prototype boards made, but to get those boards made is going to be quite costly. And at this stage, the recreation project is actually on the back burner until I can get my finances in a bit better position. But I thought a year away is probably longer than I should have been. But like I said, I had to focus on my health. My health is important. Sorry for the static image, but I haven't been able to go down to my workshop for quite a while. And I need to get my camera equipment serviced as well. So for the time being, just going to stick with the photo. So also in regards to that, in more regards to my health, the picture you see there, I have since lost a substantial amount of weight since that photo was taken. And I'm actually a lot healthier, and which is why I've gotten back into things. So moving forward, the next project I'm going to work on, I will get back to the Farming and SME series, and I'll get back to my recreation projects. I've done work on the Lyrebird project. I've done work on the mixer as well. But at this stage, I'm going to focus on a new project that's going to go more into, but will be more of a design and build versus a full conversion of an existing project. So this new project is to basically design and build a security system panel. Now, I say to people, and this is just in a most simplest term, all a house alarm is a glorified noisemaker. Now, yes, at its simplest level, that is what an alarm system is. But as my day job that I have, I do install security systems. I'm familiar with how they work and how they function. So what I'm going to do is, in a process to try and let people understand the reasoning behind security systems and how they help protect our investments, by actually going through the design process of building one. Now, I am basing this security system on an ATmega 328P microcontroller. It is only an 8-bit microcontroller, but a lot of your modern domestic panels these days still continue to use 8-bit microcontrollers. The more upmarket ones now use 16-bit microcontrollers, and your commercial ones use 32-bit microcontrollers. So essentially what we'll be building is what I call an entry-level 8-bit alarm panel, basically. And if you look at a lot of cheap entry-level panels, they still use this type of microcontroller, not specifically the ATmega. There are other microcontrollers on the market that are utilized, but they do use them, and not much has changed in the last 25 years. So basically this video is to basically go through the design methodology and also what I'm planning to do with my panel design, and try to eliminate some more common fallbacks that are used and has been used because it works, and also to explain why a lot of the technology in security systems is done the way it is done, for the simple reason as to why. So here we have, this is an example image. This is what a security board looks like, basically. Down the bottom here, you got various connections. So here is the main microcontroller, which basically is what runs the show. Now, this is an example of a Risco board. Here we've got the serial expansion bus. This is where we do expansion for adding more zones, adding keypads, adding relays, various items that would normally work on a security system. Here we got the zone inputs. Now, for most panels, the standard is 8. So with mine, I'm going to go with 8 as well. This here is the auxiliary output. So this is where power comes from that powers external devices. Now we're talking about external devices like PIRs, reed switches, and stuff like that. Anything that requires 12-volt power. Most alarm panels work around 12 volts. In this section here, we've got the bell outputs. Then this is where nowadays, instead of actually seeing a signal gets amplified and played over a speaker or a siren noise, normally it's a switched 12-volt output that activates a piezo type siren. These sirens are designed to drive people off. And this section here are what we call relay outputs. Now, these three here are what they call dry contacts. So they're basically like a type of normally open collector transistor output to power external devices like strobes, basically, or going into like a mechanical relay to open a door with 4-axis control. And of course, we've got a dry contact relay here as well, which can sometimes be used for various items like connection to a garage door motor and as such. That there is a mechanical relay. In my design, I'm planning to replace that said mechanical relay with a set of MOSFETs providing the exact same function, but in a more solid state nature. So I'm looking to go and remove as much of the mechanical type switching out as I can. Also, something I'm still at two minds about is this here. This is the PSTN connection, or public switch telephone network. Now, in a lot of the world, this has been removed from panels. It's no longer used. But here in Australia, we still use it in some aspect for monitoring of alarm panels. So basically setting, conditions of alarm panel via a method called contact ID, which was developed by Demco in the 1980s. I am still at a mindset as to whether or not I would include a PSTN type interface, but I am planning to have a serial expansion on my design. So if I want to add it on, or if people take this open source project and decide they want to add in a means to monitor the panel remotely, then they can do so. And of course, you've got your power input. Now, like I said, a lot of panels are based on 12 volt because a lot of devices, because when alarm systems were first designed, worked on the 12 volt type powering situation, because a lot of the early electronics were 12 volt based. So we're talking when the first of the alarm panels that became in regular use was in the late 1970s, early 1980s. A lot of digital electronics ran on 12 volts. Although the main boards themselves have since moved on to 5 volt and 3.3 volt logic, a lot of the external devices still continue to run on 12 volts and are designed to run on 12 volts. Not only that, because of the 12 volt nature of a lot of the devices that interact with the panel, you end up basically being able to run devices on fairly long cabling with minimal loss in voltage and continue to function as intended. Because, like I said, you're going to have PIRs, smoke detectors, reed switches, which are just a simple switch, but it's more your power devices like smoke detectors, PIRs, glass breaks, stuff like that. And by sticking to that 12 volt standard, it means with my panel design, you can still use standard devices you can buy from any security supplier. So with regards to the security panel design, I'm going to be making heavy use of shift registers. Now, reasoning I'm doing this is that the ATmega328 is limited on pins, and I need to provide a serial interface for expansion, and I need to be able to have both inputs and outputs. And also, I need to be able to actually also read the inputs in a very particular way. Most security panels work by running a 12 volts through a series of resistors at the device end. These resistors give indication of a break in the cable, alarm condition, tamper condition, and basically sealed condition. So generally speaking, most devices use 2 resistors at the end of line to detect both the tamper and sealed conditions and unsealed. The reason being is that if someone decides to interrupt the flow of voltage from the zone zones common to the input of the zone, it will be able to detect that there's been a break in the cable. With a single line resistor solution, all you're looking for is for a sealed and unsealed type situation. So when the alarm is in a disarmed state, it won't indicate there's been tampering. So that's why generally most alarm systems nowadays use a dual end of line resistor type configuration. There are some that now use triple end of line resistors. I don't fully understand how this is done, But like I said, this panel is more going to be teaching how the design works and specifically how I'm designing this panel. And a lot of the heavy lifting will be done in the firmware of the microcontroller. But by utilizing shift registers, I can have more than one input and output. Because like I said, I need at least 4 relay outputs to drive stuff like strobes and also to interrupt power to smoke detectors, cause them to go into reset, because when a smoke detector triggers, you've got to try and put it into a reset condition to stop it from sounding, because they do have their own local sounders. So as a result, I'm going to be heavily using shift registers with the Arduino, and also part of the design, I will have what I call an expansion header. This expansion header allows for local expansion of the actual panel. It exposes pretty much all the unused pins and the pins that can be connected into on the board, so that effectively you can plug in via an expansion cable additional functionality and facilities on the actual panel itself, thereby giving the ability to basically have a fully featured and functioning working alarm system. Now, this is not how most alarm systems are designed. This is the way I'm designing mine. And as a result, I also need to do this because I'm also limited for analog ADC type connections on the microcontroller, because basically I've got to send out 12 volts, come through resistors, and then read that voltage at the other end. So this also involves heavy use of the ADC as well to detect and check to see if there's alarm or tamper conditions. So as a result, there'll be heavy use of the timer in the microcontroller to constantly scan and check all the inputs. So in summarizing, essentially what I'm actually going to be doing is basically designing and building an alarm panel that basically will do the same thing as many on the market, but where I will go into my design methodology for the panel I'm designing, and basically to let people understand what goes into these panels so people can actually understand the actual cost involved, which is why they cost so much. Like, your cheap panels are still around the $400-500 mark, but there's a lot that goes into these panels and a lot of work. I will be honest, I'm only a self-taught electronics enthusiast. I've never really spent long enough at college to learn it fully, and every time I've tried to want to go back and study it, because of my autism, a lot of the lecturers tell me to go away, because I believe I can't learn in a classroom environment. So when the system's against you, there's not much you can do. But in the coming videos, as I go through, as the panel expands, you'll learn along the way what goes into these panels. I will primarily be using KiCad for a lot of my development work, and I used to have a sponsorship with PCBWay. Unfortunately, that agreement has been broken, so I'll deciding as to whether or not I will be using either PCBWay or JLC PCB to get the boards made, and then we'll do an assembly and testing of the design, and then necessarily doing any needed changes that might be needed. But keep your eyes peeled for the first step of the video, where we basically start with the microcontroller and pretty much start with the 8 input zones, including their condition reading. So until then, I'll see you next time. Bye for now.